When previous earthquakes have occurred in the past, engineers noticed that some structures had tipped over or sunk into the ground, despite the structure remaining in one piece. Sometimes buried structures like pipelines or basements would come burrowing out of the ground and onto the surface. Eventually, geotechnical engineers figured out that this was happening due to a phenomenon called liquefaction.
During earthquakes, the intensity of the shaking makes soil particles want to move, but water inside the soil reacts and builds pressure. This pushes soil particles away, reducing the strength of soil. As a result, soil behaves like a liquid so that it can no longer support the weight of structures.
Traditional ground improvement methods such as dynamic compaction, vibral placement, and jet grouting are used to strengthen soil and improve their performance during earthquakes. While these techniques have proven to be successful in mitigating the effects of liquefaction, they can have a large environmental footprint and can be difficult to install under existing infrastructure. To overcome these challenges, researchers at the University of California, Davis are exploring bio-cementation as a new, innovative ground improvement technique.
Bio-cementation leverages bacteria that exist naturally in soils to cement sand deposits. By injecting nutrients, a calcium source, and urea into the ground, a bacterial-mediated reaction produces calcium carbonate crystals. The crystals bind soil particles together, preventing soil particles from moving away from each other during shaking and therefore preventing liquefaction.
To test this new technology at a large scale, centrifuge experiments were completed at the Center for Geotechnical Modeling at UC Davis. A centrifuge is a device that spins a model in a circle to increase the force of gravity and allows a small 1-meter model to become equivalent to an 80-meter model when going at full speed.
To build the soil models, liquefiable sand was placed in the container by letting it fall from a funnel at a prescribed height. The bio-cemented soil was prepared in a block and then placed at the center of the models. Finally, a structure is placed atop of the bio-cemented block to model a real-life building.
Sensors were embedded in the model to collect data on the movements and stiffness of the soil throughout the test. As the model begins spinning, researchers monitor the sensor data to make sure the experiment is working well.
Once the target gravitational force is achieved, the model is shaken to simulate the ground movements of an earthquake. The movement of the structure in the soil is measured using high-speed cameras, and the data is then processed to determine whether bio-cementation reduced the effects of liquefaction.
After carefully examining the acceleration data, the results from these experiments show that bio-cementation can be a very effective ground improvement technique and provide increased confidence that the technology is ready for full-scale field applications.
We would like to thank all the researchers and staff at the Center for Biomediated and Bio-Inspired Geotechnics and at the Center for Geotechnical Modeling for completing this work and sharing the results with us. Thank you!